Okay, let's finish chapter 4. Here we're going to talk about the greatest common factor and least common multiple. And I know personally for myself, I used to confuse these two up so much because they're always taught in tandem, just right next to each other. It's really easy to confuse everything. So y'all be patient with yourself. The greatest common factor, GCF, or the greatest common divisor, GCD, of two whole numbers, A and B, both not zero, is the greatest whole number that divides both A and B. Now, one thing you need to remember is that greatest common factor and greatest common divisor, these are interchangeable statements. They're asking for the exact same answer. It's kind of like how interchangeable divisor and factor is. It means the exact same thing. It means that they go in and they equally and evenly divide out without leaving a remainder. We're going to go over a few methods. There's the color rod method, the intersection of the sets, prime factorization, and then finally the Euclidean algorithm. I'm not going to draw out the colored rods because you guys have seen my drawing and it's not very good. So I'm going to explain the process here. Colored rods are manipulative in almost every elementary school. They are the rods from 1 to 10, and each denomination of the rod is a different color. Okay, and this makes it really easy to build different numbers and do a lot of things. So when you're using colored rods, the first step is to model each of the given numbers. And what they kind of call them with colored rods is the train. So you build a train. So first you model each of the given numbers next to each other with some space in between, and then use smaller blocks of the same size to build those numbers as well. And the idea is to use the largest of those smaller blocks, if that makes sense. This amount allows the students to really experiment, right? So they can kind of see that, maybe a certain denomination's not going to go in evenly on that one, and they can kind of start playing with it. It's really good for hands-on learning. Excuse me. Also, there's the intersection of sets. So here we're asked to find the greatest common factor between 24 and 36. So I want you to notice this notation here. And I can't remember if it was actually used before, and it might have been used in the first unit, but this stands for the divisor of 24 and the divisor of 36. The big D means divisors. Okay, and so the first thing we do is we list out all the divisors of 24, as you see here in the list, and then I listed out all the divisors of 36. So the next thing we do is we compare the intersection of the sets, and the common numbers here were 1, 2, 3, 4, and 12. And you can see over here in the directions, the highest value of the intersection, so the biggest number in the intersection is the greatest common factor, because this intersection is a list of all the common factors. But what we're really looking for is the greatest common factor, so there we are. Another way to do the intersection of sets is to use a Venn diagram. Okay, and I know we did some Venn diagrams in the last chapter, or in the last unit, but I want to go ahead and just fill this in together here. So what goes in the middle is our intersections, the ones that are the same. So I'm going to just kind of connect them with some lines here. Is there anything else? Between 36 and 40 looks like 1, 2, 4. Nope. Okay, so in the intersection in between the two, so we'll make this guy 36 and this guy 40. And in the intersection, we're going to have 1, 2, and 4. And then to finish out the 36, any number that's not in the intersection that's over in 36 needs to go in here. So we're going to have 3, 6, 9, 12, 18, and 36. And then anything that's in 40 that's not in the intersection will go in the other piece of a circle, and that's going to be 5, 8, 10, 20, and 40. 5, 8, 10, 20, and 40. And so the greatest common divisor is the highest, the largest number in the intersection, and here the largest number in the intersection is 4. There's also the prime factorization method. So here we have an example to find the GCD between 72 and 108. So the first thing we did was find the prime factorization of each of the numbers here. You can see I kind of broke it down into the little pieces, and then I put it together. And this is tricky a little bit because here we're going to be looking for the lowest power of each of the prime factors that occur in either one of these numbers. But when you're looking for the greatest common divisor, and that greatest common divisor is comprised of the lowest power, sometimes students get confused. Okay, so the idea is as we look at the prime factorization here, and you could do it, you could totally do this before you have introduced exponents and stuff, or if you have a student that's having some difficulty or whatever, you can look at it by circling up groups. So we have 2 groups of 2, and we have 2 groups of 3, that are common in both. And so in that way we can see that the GCD is 36. But if we're technical and if we do not have all of these factors written out as I do here, and we want to look at the rule, what the rule says is you determine the lowest power of each of the prime numbers, of each of the prime factors that occurs. Okay, and so we only have 2 prime factors here. We have 2 and we have 3. Here is our 2, here is our 3, and we're going for the lowest power that occurs. And here we have a square for the cube and a square for the 2. Okay, and then we multiply them together. That gives us our GCF. Okay, so as we go along, of course, our sophistication increases, and here we're going to talk about the Euclidean algorithm, and this method exploits the theorem that describes the relationship between divisibility and subtraction. And if you remember back in the last lecture when we talked about divisibility, maybe 2 lectures ago, I can't remember, but I introduced a big long list of theorems that says, and this is one of the pieces of this theorem that had like 5 parts, and it says if D divides A, D divides B, and A is greater than or equal to B, then D divides the difference between A and B. Okay, so this algorithm is going to seem a little bit weird, but it actually is really efficient and good for those little bit older, students. Okay, so here's kind of what the rundown is. The first step we did is we replaced the difference of A minus B. We've replaced A here, so let's look here what we have here. So I have the GCD of A comma B. We've got it in the order so that A is larger than B, which is what it requires. We could change this order because that doesn't really matter. We're just looking at these common things between these two numbers. So if it's given to you and not in the correct order, that would be your first step, okay? And then it says to replace the A with the difference A minus B. So here we have replaced our 676. I'm going to put in 676 minus 221. And what we could do here is do repeated subtraction, because the idea is we want to divide out as many 221s out of 676 that we can. So we do this repeated subtraction, and I said it's kind of recursively because if we were so inclined here, we could say 676 minus 221, comma 221. I'm not going to write all the GCD stuff down there. And if we did that math there, then that would be 445, comma 221, and then we could apply this rule again, and we would say 445 minus 221, comma 221, and do that math there, and that would give us 234, comma 221, and it looks like we can take another group of 221 out here. Notice all I'm doing is repeated subtraction, which is really the core of what division is. And if we subtract here our 234 or minus our 221, comma 221, then we are left with 13, comma 221. Now if you look over here in the directions, what I just did was this repeated subtraction until we could no longer perform any more subtraction. But alternatively, you could subtract the largest possible multiple of B. Now we were able to subtract 221 3 times, so this is why my next step I just said 676 minus 3 times the 221. I did that math there, and I was able to reduce it down to this. Now 13 actually divides into 221, so we know that our greatest common divisor, because this guy is prime, is going to be 13. Okay, now don't get discouraged. This is kind of a lot to wrap your brain around. I'm going to promise you that there's a more visual way to do the Euclidean algorithm, and it's probably more the way that you're actually going to do it in class with your elementary ed students. Okay, so hold on a second. All right, so let's talk about this particular theorem real quick. If A and B are whole numbers not equal to 0, and A is greater than or equal to B, okay, remember that this condition here is the condition that allows for subtraction and division, to be quite honest, but let me just call it subtraction to be basic about it. Then it says the GCD of A minus B is equal to the GCD, sorry, my bad. It's kind of late. Okay, let me rewind that for just a second. The GCD of A and B is equal to the GCD of A minus B and B, which we just saw in that last example. Okay, it goes on to say that the GCD of A and B is equal to the GCD of A minus K, some number, a multiple of B, where K is, and this is some notation, and I can't recall if I've brought this notation up before, but the symbol of this looks kind of like a weird E, is an element of And this funky W here is just shorthand for whole number. Thought I'd just throw in just a little notation there. Anyway, okay, so, and we just saw this happen. We just saw in the last example that we were able to take multiples of B away from A until it was down to a number we could no longer subtract from. Okay? Doesn't necessarily mean it's always going to be a prime, but it has to be a number you can no longer subtract from. Okay? And I want to remind you again, the word greatest common factor, or GCF, and greatest common divisor, GCD, mean the exact same thing, because factors and divisors mean the exact same thing, and they're going to be used interchangeably. Okay, so here what we're going to do is we're going to find the GCF of 10,764 and 2,300 using the Euclidean algorithm. Okay, so and this is the way you generally use it in practice. And the first thing we're going to do, the first step, is we take the B. Remember, this guy's B. We're going to take B and we're going to divide it into A. Okay, and we're just going to do this quick division here, and 2,300 goes into 10,764 4 times, and when we multiply that through, this leaves us with 9,200, and we're going to do that subtraction. Now, this number must be smaller than 2,300. Okay? All right, and now, and this is kind of like the weird part. This is kind of like the weird part. So just hang on. Now we're going to take that 1,564 and we're going to divide it into the 2,300. I know this is crazy. Just trust me. This is what we do. Now 1,564 will go into 2,300 one time. Doing that subtraction there, and that leaves us with 736. Now we do it over again. Now we're going to take that 736, it becomes the divisor. So basically the remainder becomes the previous divisor. The remainder becomes the previous divisor. I'm going to write that down so I don't forget to say that. So the remainder divides the previous divisor. Okay, and so we keep on doing this. Let's see, this goes in 2 times because 7 times 2 is 14, so it should fit. Let's see, and if we do that math, we get 1,462. Subtract that, we're left with 92. And now we're going to do it again. 92 divides into 736. 92 goes into 736 7 times. That is 644. Do that subtraction. Hopefully I can get it to fit right here. That leaves us with a 92. And now we've got one more. Now that 92 is going to divide into that 92 one time with a 0 remainder. Now, once you get to that 0 remainder, the final divisor of the Euclidean algorithm is the greatest common factor. So the greatest common factor of our 10,764 and 2,300 is equal to 92. Okay, I encourage you to practice that and, you know, come back to it. See me if you need help. Send me an email. Ask me for more examples. Anything I can do to help. All right. Okay. So that ends the greatest common factors. Let's take a look at the least common multiple. Okay. The least common multiple, or the LCM, of two non-zero whole numbers, A and B, is the least non-zero whole number that is a multiple of both A and a multiple of B. There are several methods, of course, and here are a few. There's the measurement method, or the number line. We've done that before, a lot of that in chapter 3. There's colored rods, which we talked about a few minutes ago. There's the intersection of sets, which we've seen, finding the GCF, the prime factorization, which we've been doing and have now been using to find the GCF, and the Euclidean algorithm. So here's an example of the measurement model, or the line model, and what we do is we draw multiples of each of the given number, one stacked above the other, like we've done with addition and subtraction and multiplication. And the first place that the sectioned multiples actually line up at is the LCM, okay? And so you can see here that they lined up at 20. And we could continue this off, and they're for sure going to line up again at 40, which is 2 times 20. So we could extend this out. And the colored rod method is going to stack up very similarly to this. You would make and I can't remember if I explained it. I don't think I explained it, but you would make a train of, say, in this case, four, 5 rods, and then you would see how many. Well, I can't explain it. I'm sorry, don't make me re-record. I'm 23 minutes in. Please excuse me. I should not record 2 in one afternoon. I'll guarantee you that. Okay. All right. So just know that the color rod situation would work similarly. You would continue to put out trains of the 4 rod and trains of the 5 rod until they both met together. I knew I could finally say it, but I just couldn't say it a moment ago. Okay, until they finally met together, and then you would count to see at what point did both of those meet. Okay, blah. Sorry. Here we go. The intersections of sets. Okay, so here it's just like finding the GCF with the intersection of sets, except for here we're looking at multiples, so it does not make any sense to list the factors. Here we're going to list all the multiples. Okay, so Here I've got an example, find the LCM between 8 and 12. I have listed out the multiples of 8. Of course, this is an infinite list. The divisors are not an infinite list, but multiples are an infinite list. So I have not listed out every possible one. I could have made these lists longer, but I didn't want them to go multiple lines. And then after you have listed out a reasonable number of multiples of each of the number under investigation, then you're going to look for the intersection of those sets just like we did before. And let's look here. Our first pair that intersect is 24, and then it looks like 48 is also a pair. And I didn't go much further, but I'll tell you the next one would be 72. So here is the intersection of the two sets, and for the least common multiple, least common multiple, we're looking for the smallest of the multiples, and that's going to be 24. Okay, when we go to looking at it in the sense of the prime factorization here, then let's look at an example. The LCM between 2,520 and 10,530. Okay, so the first thing first is we're just going to find the prime factorization of the two numbers. As you can see here, I've already found the prime factorization of each. 2520 or 2,520 is 2 to the third power 3 squared times 5 times 7. 10,530 is 2 times 3 to the fourth power times 5 times 13. So when you're doing this with the prime factorization, we're looking for the highest power that occurs in each of the factorizations. So this again is, where that confusion happens, because these guys are taught in tandem. The greatest common factor asks us to find the lowest power of all of the common factors, but the least common multiple is asking us to look for the highest power, and so it's just an opposite in your brain. All right, so if we look here, in between the two, it's asking us to look at the highest power. Well, we both have 2, so for the power of 2, the highest power was a 3. For the prime of 3, the highest power was a 4. For the prime of 5, there was no power expressed, and remember, if there is no power, that power is implied to be 1, so these are all actually to the power of 1. And when we multiply these numbers together, then this gives us our least common multiple. Now, if you needed to just find a common multiple, you could always multiply the two numbers together, but that is different than having the least common multiple. If you're looking for the least common multiple, then you're actually going to need to craft it out this way. Okay, let's make the connection between the greatest common factor and the least common multiple. There's a theorem, of course. So for whole numbers a and b, the greatest common factor of a and b times the least common multiple of a and b is actually equal to a times b. Okay, remember, the greatest common factor is going to just give you a value. The least common multiple is going to just give you a value. These two values are actually going to be equal to the a times the b. Now this is super powerful because of this form, and we've got this multiplication going on here. This can all be really, really manipulated algebraically to solve for a lot of things here. Right now, all we're going to do is just use this to solve if we're given a GCF to find the LCM. but technically we could find all sorts of things here as long as we're given enough of the values. Okay, so let's look here for the steps for the Euclidean algorithm. What we do is first we find the GCF using the Euclidean algorithm, and then we're going to use a manipulation of this theorem here, and I've given it to you in two forms that we could use it in. If we were given an LCM, we could find the GCF. If we're given a GCF, we could find the LCM. Now, the truth of the matter is it's easier to find a GCF because they're not infinite as far as being common. So those are finite lists that are much easier to manage. So most often you would be looking for an LCM using like an Euclidean algorithm here. Okay, so find the LCM of 952 and 731 using the Euclidean algorithm. So first I have the GCF written here, and then I've done the subtraction. So remember that this is A and this is B, and so I can do this A minus B comma B thing, and I can repeatedly do that until there is a number smaller than I can subtract from. So I have done that, and at this point, to get to the end, so I've done this first step just to make my numbers bigger. We could have jumped off right here at 952, but I was able to actually make the numbers a little bit easier. So at this point, I can go 221 divides into this 731. And how many times does that happen? That's 3 times, and that's going to be 663, and we're going to do that subtraction there, and that's going to leave me with 68. And then we're going to take the 68, we're going to say 68, and it's going to divide into the last divisor, 221. 68 goes into 221 3 times. That gives us 204. Make our subtraction here. That leaves us with 17. Now we've got another one here. We're going to take our 17 and we're going to say 17 divides into 68. 17 goes into 68 4 times. 4 times 17 is 68, leaving us that sought after 0 remainder. And so that means that the last number that was the divisor is the GCD. So we know our greatest common denominator of our numbers, 952 and 731, is equal to 17. And now we're going to plug that into our equation here, and our equation is this. Okay, and then I did the math here, and our answer is 40,936. Okay, so the idea with using the Euclidean algorithm is to find the GCF using the Euclidean algorithm, and then taking advantage of that theorem and the fact that the GCF times the LCM is equal to the two numbers that are being under investigation for the GCF and the LCM, and that allows us to get this. Okay, and then finally I've got one more problem here, and I've worked it out and wrote in a whole bunch of notes here. Given a GCF A and B is equal to 18, and a LCM of A and B is equal to 720. So these are the same A's and B's. These are two numbers that are related. They give it to you together, so you are to assume that these guys are related. Asks us to find all the possible values for A times B, and that seems pretty overwhelming, but we just need to break it down. So first off, we're going to find the prime factorizations, okay? Because we're going to lean on the definitions of GCF and LCM to figure this out. So I have figured out the prime factorizations of 18 and the prime factorizations of 720. Now we're going to use what we know about GCF, and remember the greatest common factor is the least powers, and the LCM, which remember is the greatest powers of the prime factors. We can say that one of the numbers is going to have a single power of 2. They're both going to have 3. So let me show you why I say it. One of them is going to have a single power of 2 because the GCF says that at the minimum, because the GCF isn't 2 squared, it's 2. So one of them can only have one power of 2. Okay, so one of them must have a single power of 2 because of that GCF. They both, for the same reason, because of the GCF, they both have to have a 3 squared in it because that is the definition as well. Okay. Now, either one of them can actually have this 5 because the LCM means that it could be on either one. The GCF is the common, the LCM is listing all of them and at the highest power that they're listed in either of the factorizations. So, I know this might feel a little bit confusing. So I'm going to try to, sorry I was losing my papers there. I'm going to try to clear it up. So we have a couple of situations here. We have to have a single power of 2. In one of the numbers, we have to have that single power of 2. And since the 5 can go with either one, we're going to have 2 different situations. They both have to have the 3 squared. So here's our 3 squared. And that number, and I'm sorry that the comma is not very clear, but there's a 3 squared in the second digit of each pair as well. And then we just have to have a 5 in one of them. Now, all the pieces of the LCM have to appear here, but you can see that the way to do it is to first set the GCF because that's the more restrictive of the 2. You want to decide what needs to be in each of the digit. Now I want to make sure that you see that I actually have 2 digits here. Here's the first digit and there's the second digit of each of these pairs. Here's the first digit, there's the second digit. Okay, so first we're going to set the GCF, and then you can move the factors around that aren't set. Okay, so the GCF really kind of runs the bus on that, and then the LCM kind of brings the flexibility. Okay, now these are the only arrangements that'll fit the criteria imposed by the GCF. All right, well, we did it. We have finished chapter 4. We'll move on to chapter 5. I hope you guys have a nice day. Thanks.